Rebecca and I are here today to talk about tools that we've developed to balance stakeholder objectives for restoration and conservation of floodplains in the Lake Champlain Basin, and specifically in the Vermont portion of the basin. Before we get started, we would like to acknowledge our many co-investigators and students that have worked and contributed to this Sea Grant project. Our work has been seeded by many other additional sources of funding that you see there below. And as we'll see in this presentation, the research that has been enabled by Sea Grant funding for both of us has itself contributed to the Vermont Functioning Floodplain Initiative. The tools that we'll be introducing today have been developed with support from two separate Sea Grant projects awarded to myself and Rebecca, and we'll both be reporting out on some of the key findings from these projects today. Integral to both of the projects are floodplains, and so I just have a few introductory remarks about floodplains and their value. When rivers are able to flow into their floodplains during a flood, and the energy of the water is dissipated, that can reduce erosion along stream banks and serve additional floodplain functions of value to society. Connected floodplains store floodwaters, sediment and debris and ice, reducing flood damages in downstream reaches. Floodwaters can recharge underlying groundwater to increase our resilience to drought and dry spells. When they're free of constraints, rivers have adequate space to meander and achieve minimally erosive planform and dimensions. And today, when we speak of floodplains, we're really focused on what might be called the geomorphologic floodplain, that stretch from valley wall to valley wall. So not the regulatory definition that you might be more used to seeing referenced on a FEMA flood insurance map, for example. Historically, we've made land use and channel management choices that have disconnected our rivers from their floodplains. Could be laterally or vertically or both, or even longitudinally upstream to downstream disconnections, or temporally across time. Encroachments within our rivers and floodplains led us to manage rivers through channelization and dredging, berming and armoring in order to protect those riverside investments like rails and roads and buildings. And the resulting disconnection of our rivers has enhanced nutrient and sediment flux to receiving waters. It's also caused our rivers to become more transport dominated and susceptible to catastrophic erosion in big flood events. The repeated cycles of channel management following flood events have cost many millions of dollars to our small state, and these actions are not sustainable over the long term. So over the last 20 years or so, Vermont has embarked on a new river management strategy that recognizes rivers as dynamic systems that need space to adjust to changes on the landscape. And in keeping development out of the river corridor, it's a very cost-effective strategy to both increase our resilience to flooding and improve stream stability, ultimately leading to improved water quality, as we're mandated to do under the Lake Champlain TMDL. Vermont began to recognize that the ecosystem co-benefits of connected floodplains added to the value of river restoration projects and began to identify opportunities to reconnect Vermont rivers as early as the mid-2000s. Many of you here on the call, including state and federal agencies, conservation districts, watershed groups, engineers, consultants, have been involved in projects over the years to lower floodplains, replace undersized crossings, or reconnect flood chutes, for example. Often these projects were identified in the context of a river corridor plan, following guidance from the River Management Program and Mike Klein. And beginning in about 2019, under Mike's leadership, the Functioning Floodplain Initiative was formed as a kind of a reimagining of this ongoing restoration and conservation work to cast these efforts in a broader framework of reconnecting Vermont's rivers, to more systematically identify those highest priority locations for reconnection. Kind of a next generation river corridor planning effort, if you can think of it in that way. And so the overall goal of the FFI is to achieve the highest possible water quality, ecological integrity, and flood resilience by targeting our restoration and conservation projects where they can be most beneficial. So over the last couple of years, the Vermont Functioning Floodplain Initiative has developed a decision support system implemented in a web-based framework where we're analyzing the lateral and vertical floodplain connectivity, as well as the longitudinal temporal stream connectivity. This has been performed for streams draining greater than 2 square miles in the Vermont portion of the Lake Champlain Basin. These data inform then the selection and the prioritization of reconnection and conservation projects. The FFI framework allows users to estimate the water quality benefits of a particular floodplain or river restoration project in terms of reduced phosphorus loading, and also the economic cost benefit of the same project in terms of improved resiliency to both inundation and erosion flooding. A future build out of FFI will also permit estimates of habitat benefits resulting from improved river and floodplain connectivity. So our Sea Grant research here at UVM has been integrated into this FFI framework in many ways, and will continue to be in future years, we hope, as we refine our models. So I'm going to just provide a very high-level view of how some of our research products have been integrated into the FFI, and then I'll turn it over to Rebecca to talk through a few more details on a couple of those tools. To comprehensively map floodplains in the basin, a data set that didn't exist before a couple of years ago, Rebecca has led a team to develop a low complexity hydraulic modeling approach based on height above nearest drainage maps derived from high resolution digital elevation models. And Rebecca's going to talk more about these maps and how they were developed in just a few minutes. Unlike floodplains that you may be used to, these probabilistic maps illustrate the likely inundation extents of various size storms ranging from 2-year to 500-year. So on this graphic here in dark blue, that's the 2-year storm inundation extent along a stretch of the Mad River, followed by a lighter blue, that's denoting the 5-year flood, a yellow for 10-year, orange for 100-year, and finally kind of a rust color there for the 500-year flood. We're using these maps to estimate the value of infrastructure exposed to inundation flooding hazards. And as Rebecca will talk about in a little bit, the relative inundation frequencies on these floodplain maps can be used to evaluate the sediment and phosphorus storage capacity and identify opportunities to increase the retention of nutrients in floodplains and wetlands. You may all have seen me present at a previous Sea Grant webinar about the machine learning approach that I use to classify the variety of river types that we have here in the state, each exhibiting varying states of connectivity, either due to their natural setting or as a consequence of past disturbances. We know we've been able to classify at least 6 different connectivity classes applicable to the wide range of stream types that we see here in Vermont, from those steeper gradient confined settings with limited floodplains, all the way down to lower gradient unconfined settings with larger floodplain development. I won't say much more here except to note that our stream type classifications are being used under the hood, so to speak, of FFI to guide the project selection that is appropriate for each reach, and also the prioritization of those projects. To evaluate the potential for flood erosion hazards, our PhD student, Jeremy Matt, has developed a really novel approach that uses the LiDAR-derived topographic information that we benefit from here in Vermont and the data sets from the floodplain mapping to estimate stream power for individual reaches. Here's a plot for one reach, again in the Mad River, that shows how stream power increases as flow rate in the river increases. From patterns in these plots, we can also see where that stream power drops as flow spills out into the floodplain. Each reach has a unique curve that looks something like this. And Rebecca and I are currently engaged in research to use these stream power curves or a similar topographic signature to better understand which reaches and which settings are more effective at attenuating floodwaters. Our master's student, Scott Lawson, has adapted Jeremy's approach to generate stream power curves for all the reaches in the Vermont portion of the Lake Champlain Basin, at least those draining greater than 2 square miles. And for those alluvial reaches that have field-based stream geomorphic assessment data, the ones that are colored in red on the map on the left, we can use the grain size distribution data, those pebble count data that you may be familiar with, to evaluate how susceptible each reach is to erosion during storms of various sizes. So that's an ongoing piece of work, but under the hood of FFI at present, we do have at least a preliminary assessment of how susceptible each reach is to erosion based on these very curves. We can also simulate restoration and conservation projects using hydrodynamic models like two-dimensional HEC-RAS models. And my former student, Lindsay Worley, did that as part of her PhD dissertation. With help from Friends of the Mad River, we chose 11 different floodplain reconnection and wetland restoration modifications in the Mad River watershed, combined in 6 different scenarios. And we then simulated river flows with the HEC-RAS model under various storm sizes through these modifications to examine how well each project stored floodwaters and attenuated flows. We estimated the phosphorus stored in reconnected floodplains relying on a statistical method that Rebecca will touch on in a few minutes. And we also quantified the socioeconomic impacts of these projects as a sort of opportunity cost of restoration and conservation in terms of a lost development potential. So in summary, because of the steep setting of the Mad River watershed and the flashy nature of flows in that watershed, we did detect only modest attenuation of peak flows under a 2-year, 25-year, 50 and 100-year design storms. But several scenarios of floodplain reconnection more than met the necessary annual phosphorus load reductions that were targeted for the Mad River watershed under the Lake Champlain TMDL. Also, as part of her dissertation, Lindsay created a basin scale optimization algorithm that uses the geospatial database that is FFI. You can think of this algorithm as kind of being wrapped around the FFI geodatabase. And we generated scenarios of river reconnection or conservation that will optimally meet multiple stakeholder objectives. In order to get a sense for what those stakeholder objectives are, we actually did a survey with the help of my colleague Dana Rowan-Gould in SEMS and her student Danica Didioko. And Lindsay, of course, we issued this river survey to 60 river professionals that work actively in the Lake Champlain Basin in Vermont, and to get a sense for how they ranked various river project objectives. And you can see here that flood resiliency and safety and water quality both ranked quite highly among this group of 60 professionals. So we used these river project objectives and the responses from these river professionals to weight objectives in this multi-objective algorithm that we wrapped around the FFI database. And so, for example, each of the dots on this 3D diagram on the right-hand side connects to a unique suite of restoration. It could be, for example, the blue dot the dot I've circled in blue here might hypothetically represent 3 different reaches along a stretch of one of the tributaries of the Winooski River Basin. And each of those dots represents a valid solution to this algorithm. A suite of projects that's located about where letter A is pointing to would be one that was very effective in terms of storing floodwaters and storing phosphorus in the floodplains, but might have an associated high socioeconomic impact, meaning that we may be using floodplains that were also valued for other purposes like development or agriculture. So this is a tool that is available in kind of a beta form and could be used in a future version of FFI to further refine the priorities for projects that are selected in the planning tool of the Functioning Floodplain Initiative. And so I'll stop here and I'll let Rebecca take over screen sharing, and she's going to be providing some more details of a couple of these two tools, and namely floodplain development and ways to estimate how much phosphorus can be stored on these reconnected floodplains.
Great, thank you so much, Kristen, for that. So as Kristen said, I'm gonna dive into some more detail on 2 pieces that Kristen went over on the research that we've been engaged in that's informing the FFI, or the Functioning Floodplain Initiative, and informing kind of management of floodplains in general. So as I started to work on floodplains in Vermont back in 2018, it became apparent that sort of as a starting point, what we needed to understand the distribution of what we call geomorphic floodplains in the state, in the Lake Champlain Basin in particular, and to understand how hydrologically connected they are, or sort of, how often are they flooded. Over the years, we worked on this problem and recruited a handful of students to develop tools to identify floodplain boundaries, as well as the frequency of inundation, again, for rivers draining the Lake Champlain Basin. So as I said, this work started in 2019 and culminated with a data release in 2022 that the UVM, or sorry, the Sea Grant releases in the chat for your interest. So traditional methods of floodplain or flood inundation mapping tend to use hydraulic models, which can be computationally and data intensive, and therefore they're really hard to execute at scale. And so when we want to create these maps of the entire Lake Champlain Basin, this becomes problematic. And while the state has some coverage of FEMA maps, as we know, they're limited spatially, and they do not provide that granular information on inundation frequency across that geomorphic floodplain. That's important for us as we study floodplain processes. So instead, we look to a new generation of what we call lower complexity models that typically simplify hydraulic processes. And in the case of what we ended up using, take advantage of the existence of high resolution, widely available information on topography. So the approach that we used relies on what we call a hand map, which stands for height above nearest drainage, or essentially the elevation above the channel bottom. And so you can see here this example out of Texas, DEM, or digital elevation model, where the absolute elevations are greatest in the headwaters and the lowest as you move to the outlet of the watershed. When you then quantify sort of that relative elevation above the channel bottom, you can see that channel network rise up, and you can see these light blue areas as the lowest points on the landscape, and everything as you move away from them as having a higher elevation. And so that's our hand map. And so to identify floodplain maps from this approach, what we first did is take that DEM for the state of Vermont and convert it to a hand or a relative elevation map, as shown here. The next step in this process is to then build what we call a rating curve for different stretches of river or different reaches that relates stage or hand elevation above the channel bottom to discharge. And so that's what we are looking at here with this stage discharge rating curve, and we use the empirically based Manning's equation to develop those. The third step is then to translate that rating curve to a floodplain or an inundation map. And so to do this, what we did is we used flood frequency relationships that relate the flood return period here on the x-axis to a discharge. And we can use these three pieces of information again to create the floodplain map. So as an example, if we want to identify the inundation extent of a 2-year flood, we associate that with a discharge of approximately 2,000 cubic meters per second. And then we look to the stage discharge rating curve, and that's associated in this area with a stage of 4 meters above the channel. And so we fill in those spots on the landscape and identify which bits of that landscape are inundated during that flood event or that recurrence interval flood. We can do that similarly for a 10-year recurrence interval flood and a 500-year flood. And this together creates our what we call sort of our composite map, or our floodplain maps of depicting the geomorphic floodplain and the relative inundation frequency. So as I said, in 2022, we finalized the most recent version of these floodplain maps. We did this for all streams that drain to Lake Champlain here in Vermont, that drain greater than 2 square miles. They range, as Kristen noted, from anywhere from the 2-year flood, showing the extent of that, to the 500-year flood, shown here in red. These maps, as I said, they exist. They're also publicly available for download through the VCGI. And because of that, we kind of want to make it clear, and there's documentation within the data release on VCGI about this, that these are developed to support conservation research and planning, such as what we're showing here for the Functioning Floodplain Initiative, as well as other applications, but they're not regulatory, right? They're not meant to replace a FEMA map. And as Kristen showed, they are serving as a base layer for a variety of different functions within the Functioning Floodplain Initiative, as well as serving as some really important information in terms of phosphorus deposition estimates, which I'll go into here in a minute. And so that brings me to the other piece of work that I want to spend just a few minutes talking about. So we've also been exploring the question of, right, how much phosphorus can a floodplain capture, and what describes this variability in differences in phosphorus deposition and phosphorus retention. So when we started this work in 2019 here in Vermont, our understanding of floodplains as phosphorus sinks was mostly derived from work outside the region. There's a pretty rich literature in the Chesapeake Bay, as well as elsewhere, as well as some modeling studies done here in Vermont. So we wanted to kind of build on that and build an empirically based understanding for the Lake Champlain Basin. And so what we did in 2019 was we established 20 monitoring sites to track the amount of total phosphorus deposited on floodplains. So each monitoring site, shown here as red squares, consists of a series of what we call turf mat plots. And that's shown in an example here on the picture on the left, where these orange squares at a site, this is actually along the Winooski River at the Intervale. These orange squares are each a plot. Within the plot, there's 4 what we call turf mats, literally just a piece of artificial turf secured to the ground. And they served as what we call surface markers, or evidence of this existing surface prior to a flood event. We've been monitoring these sites for 4 years now and have built a robust data set. And through the Sea Grant work, we're continuing to monitor the sites and refine our understanding of phosphorus deposition on floodplains, but also to work to build a longer-term data set. So we're looking to kind of increase the number of years and the number of observations, the differences in flood types, and just sort of continue to refine that understanding of both the spatial and temporal variability. Additionally, this past year, we're looking to kind of even further that kind of temporal aspect and understanding. And we went to 2 sites in particular and collected floodplain cores. And these are being currently analyzed for radionuclide activity. And this gives us a decadal scale picture of deposition dynamics. So anywhere phosphorus and sediment deposition rates between 50 to 100 years is what we're really going for here. And with that, we're going to start to kind of compare, right, these modern deposition rates that we're looking at and that we're building an understanding of with sort of the longer term dynamics and how they compare and what the variability, where there might be variability and why, in terms of changes in land use and changes in climate and changes in runoff patterns. Finally, what we're also doing in terms of thinking about floodplain monitoring and building this story here in the state is we're integrating data that Kristen and I, as well as Eric Roy, are involved in, working at 5 wetland study sites that is part of an NRCS funded project. At these sites, we're looking at a similar particulate dynamics, but because there's sort of different processes that may be important, we're also looking at dissolved phosphorus at these wetland sites. And so we're working on integrating these spatial and temporal components as well as these different phosphorus mechanisms. So as I said, we've been monitoring these sites for 4 years. So after these 4 years of monitoring, we've collected more than 200 unique observations at a plot for a given flood. And that's following about 13 different flood events that we've been able to capture. And what we're finding, as to be expected, is that there's a good bit of variability in how these floodplains function. And that's, again, is sort of what we expected to find. And so to kind of dig into this, we're looking at why this variability exists. And so what we're finding is sort of across a floodplain. So here we're thinking about what's going on sort of at a given site, and variability sort of locally on the order of kind of a 1 square meter scale. This variability is best described by the connectivity of the floodplain to floodwaters. So you can see that what we're measuring is between 0.1 to 41.1 grams of phosphorus per square meter per year. So a huge range. And you can see on this plot here, so this is that same site along the Winooski River down at the Intervale, is you can see that the greens represent high phosphorus deposition rates, and that grade to brown, which are quite low phosphorus deposition rates. And you have this really distinct, strong signal of deposition quite close to the channel. And as you move and increase your distance to those floodwaters, you decrease those deposition rates. As well as, so we've got sort of this location, this proximity to floodwaters, how close they are. But we're also finding that as we overlay our floodplain maps and gain this understanding of that inundation likelihood or that inundation frequently, that we're seeing a really distinct signal sort of over that longer period of time with areas that are likely to be inundated regularly or every year or every 2 years, having a much higher deposition rate than those that are inundated less frequently. So this value on this x-axis, annual inundation probability with a value of 1, again, understanding that that is places that we expect to be inundated almost every year, scaling back to 0, rarely inundated. And then this is kind of hard to read, but basically this dashed line, you can think of this as sort of an average measured deposition rate. And so as you increase the frequency of inundation, you can see we jump above that average line and we get significantly higher deposition rates. And so the moral of the story is here, like kind of locally, what we're seeing really driving the bus on that variability is this hydrologic connectivity. How close is it to floodwaters? How frequently is it inundated? We then take that kind of to the next scale and we look at deposition rates on a floodplain. So now we're looking at an average deposition rate at a given site. So for our 20 sites that we've been monitoring, now we still see a good bit of variability. That variability is reduced now because again, we're sort of averaging out across these plots. So now we're at 0.2 to 6.5 grams of phosphorus per square meter per year. And this plot is just sort of summarizing that at the different sites. And what we're seeing at this watershed scale is that valley setting is really important. So hydrologic connectivity remains an important factor determining deposition rates, but we're also seeing that things like valley width, slope also are really important in determining those deposition rates. And so for the Sea Grant project, we're continuing, like I said, we're continuing to monitor, we're improving the functionality of a lot of our monitoring sites. We're also continuing to refine our understanding of phosphorus deposition on floodplains and wetlands, but we're also looking at ways to continue to integrate the information into the FFI or other resources that are related to the FFI that other stakeholders can access sort of in conjunction. So the current formulation of the FFI includes a project prioritization scheme that helps to rank areas where restoration or conservation will best help meet water quality goals. And currently in this formulation, the FFI includes an estimate of about 10 to 20 pounds per acre, no matter where in the watershed we are. And this actually is supported by our observations as we average sort of this variability across the watershed. We find an average deposition rate of about 12.5 pounds of phosphorus per acre. And so it's just kind of showing that over time, right, we've built up this data set and now we support these estimates. But what we are working towards and what we want to do, and then ideally what we're going to get to, is working to use our understanding of how spatially variable phosphorus deposition rates can inform sort of a more specific identification of phosphorus deposition. Such as shown in this example that we developed for the Black Creek, where we identified phosphorus deposition rates for what we call these sort of FFI units, or the kind of these units of floodplains or small segments of floodplains. And we can see, based on their setting and based on their hydrologic connectivity, we've kind of ranked it from low to high. And this is for existing conditions. We can play the game of improving hydrologic connectivity because we know that that's a really strong control on these deposition rates, and look at the potential retention rates or deposition rates. And then we can also look to see kind of what the difference is between potential and existing to identify kind of areas that might be sort of ripe for restoration projects. The other piece that we're sort of looking to take our data and help improve upon and improve the functionality of the FFI is using our phosphorus deposition data set to support a different phase, the project design and implementation phase, where we have a list of potential projects and we further vet them using more granular information on phosphorus deposition. So provide an example here showing a proposed floodplain lowering project at Potash Brook, where you can see sort of in the design here, we have an example lowered floodplain along the right bank. And using the phosphorus, the information, sort of that spatial information we're developing with our phosphorus data set, we can see that we can kind of vet how a given proposed design may change and may improve phosphorus deposition at a site. And so this is something else, another piece that we're working on to try to kind of come up with a protocol for improving upon sort of that project in design and implementation phase. So that's a lot that we threw at you. And all of this work has led to numerous publications and data releases, reports, and I know that myself and Kristen, we posted some of them in the chat. We also have a bunch of publications that have come out in the peer-reviewed literature, as well as, again, other reports that are available online that we definitely encourage you to look at too. Of course, you know, always reach out with questions, but this work has produced a good bit of information to date. But I also want to sort of point out that sort of as we've talked about this, you know, this is also leading towards additional work, and we're continuing to work on this, and this is always in progress. And so we're leveraging this foundational work to continue to push forward our understanding of floodplains and to continue to develop tools that we can take the great information we've been collecting and create great, you know, planning and conservation tool sets. So first of all, right, we've mentioned the FFI is to be released soon, but we'll continue to work on it and refine our models and how that informs how the FFI is used. There's habitat that's about to be, we're starting to kind of incorporate it, potentially expanding the data sets to Lake Memphremagog or Connecticut River Basin, et cetera. Kristen and I, as well as Eric Roy, as I mentioned, are also continuing to work on wetland functioning and as part of an NRCS SEEP project focused on agricultural watersheds in the Otter Creek and Lemon Fair. And then, as Kristen mentioned briefly, we are also starting in on a big effort under the Cairo initiative to look at floodplains as flood attenuation zones and to incorporate that into the national water model. And we've started working in Lewis Creek, but we're going to look to expand kind of our test beds here in Vermont. And so with that, thank you for listening and happy to answer questions.